Some other stuff me and Danny did together. So presentation is about to measure vertical velocity speeds and the updraft is one of the most important elements in this uncertainty, and therefore measurements of the updrafts are necessary. So sensitivity to aerosols is quite large. Methods are usually limited to 1,000 lidars and to aircrafts and measurements by air, which are very good and sometimes are accurate, but are limited to in space and are expensive. And they're not good in the long run. So the obvious thing to do is to try and develop satellite-based approaches. There are very few. And all of them are in a very large scales, not of a single cloud, or not a scale in which updrafts actually occur. So this is the three-dimensional velocity vector, and this is the divergence operator. So if we assume that it's constant, that the density is constant, then we get the volume continuity equation, which states that the change of the updraft or of the vertical wind with height is equal in opposite direction to the horizontal divergence. And and here you can see that that solving this equation is hard, even though it's a very simple equation. And we're using a very simple approximation. We're saying that in stratiformic clouds, we had to collect data, we had to calculate the divergence at the top. We had to figure out what is the right averaging area. You talked about averaging area. This is the thing is it's a new field. Like before this method, usually people talked about averaging latitude, like one latitude over one longitude, and averaging over cells or even finer fractals of the cloud is something nobody actually did, and therefore we had to understand what is the right averaging, and in addition, what is the right layer, in which the theory actually holds, and then compare the results. So, so the data was a long process to produce, with the help of Kobi Spond here and Professor Alexander Hein. We received models of Erez Cornus, less spaced. And therefore, we had the three-dimensional models with everything we needed, with 3D wind, U, V, and W, and liquid water content, and effective radius over time. And from that, we used a rendering approach, which is called Shlom. It's a spherical harmonic approach, to simulate real imaging of clouds. So this is not a real image. This is an image we simulated from this model, as if we're taking the image from above, from a satellite, from directly above. This is the data we worked with. We actually worked with other larger simulations that we got from NOAA, from John Kazil and Feingold, and you see in the future. In addition, we worked on real data, on the corresponding data between magic operation, which is a ship that for half a year in 2013 did back and forth from Honolulu to Los Angeles and measured updraft and vertical velocity and other attributes. And but nonetheless, we saw that we can actually achieve good results. I'll explain this table, why is it good. So you see here, I'd say this is like, we took a lot of algorithms, optical flow algorithms from the recent 10 or 12 years. And this is like, I would say, an evolution of advances in optical flow in recent years. And you can see that I say EPE is the endpoint error. If I have the ground truth of the optical flow, the actual U and V movement in the image, and I have my predicted U and V, then it's just the Euclidean distance between the ground truth and my prediction. So the Euclidean distance, you can see it really improves, and we can actually get sub-pixel precision. This is in pixels. So we can get sub-pixel less than half a pixel for movements in the average of 5 pixels in Euclidean distance. Some movements are larger, like 10 pixels and such, but this translates to approximately 10% accuracy, better than 10% accuracy.
When it's large, it means that the error is small. When EPE is large, then the error is small.
So this is just an example of